Hello, happy December 20th. Back on December 6th, I promised to tell you a bit more about lepton universality. I said it was one of the fundamental symmetries that we see in the standard model, and that there's only one piece of evidence against it at the moment. And that evidence is what's known as the gyromagnetic ratio of the muon. Now, the gyromagnetic ratio tells us how different particles interact with magnetic fields. So what we do is we send a particle, say an electron, through a field, and then a photon can interact with this electron. And what we can do is use our measurements and our theories to predict what kind of effects that will have on the electron. And this gets expressed as the gyromagnetic ratio. We'll call it G. And it's 2.00 something 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 something. And this something 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 is predicted by the theory, and it's also measured by experiment. And so what we generally do is measure G minus 2. We already know where the 2 comes from. That is fairly straightforward quantum mechanics. The rest of it comes from interference from second order processes and even higher order processes. And that's the bit that we want to measure. Now, the theory behind the electron and its interaction with photons is very well understood. The electron comes in, the photon comes down, some things can happen in the middle. We can make the electron can radiate a photon, which makes an electron-positron pair, which annihilates, goes back into a photon and meets the electron at the other end. And that's a higher order process, right? Because the electrons come in, radiated the photon, hit the photon that we fired at it, gone back and has reabsorbed the photon. And that's a higher order process, and that is what leads to these extra corrections. Now, this has been calculated at great human cost, I must say. There's a lot of labour has gone into making these calculations, with pages and pages of text and equations, and then later on great computing cost as well. A lot of hours have gone into these calculations, and they got to a precision of 12 decimal places. And the experiment has kept up with that. The experiments have actually measured 12 decimal places as well, and they agree. They agree to 1 part in a million million. And that is one of the most precise measurements made in the history of science. And that looks fantastic. You think, wonderful, this is perfect, this is exactly what we expect. It shows that we've got our theories correct. Unfortunately, it's different for the muon. When you take the muon calculation, and when you pass a muon through a magnetic field and see how it interacts with this photon, there's a disagreement of 3 sigma with the standard model. Now, the probability that that is due to statistics is less than 1 in 1,000. And this is possibly the strongest evidence we have that there's something else going on beyond the standard model, that there may be some other kinds of particles interacting with this muon. So what happens is, the muon comes in, it radiates a photon in the same way that the electron can do, it interacts with the photon we fire at it, but then the photon that's come off down here can form other particles. It can form hadrons, it can form other muons, electrons and so on. And when we add up all the bits that we know, it comes out slightly wrong. The implication is that there is some other particle in this loop, some new particle we've not discovered yet. So that's what makes this so exciting. And that is the best evidence we've got that lepton universality is violated. So keep your eye on the G-2 measurements of the muon, because we're going to see some interesting things happen as we get access to greater computing power and access to more CPU time. We're going to see the theory catch up to the experiment, and then we're going to see the experiment get improved, and then the experiments will catch up with the theory, and so on. And this will tell us something very interesting about what can be contributing to this disagreement that we see between the standard model theory and the experimental results. Okay, I'll see you tomorrow.